It's what we live for. So this is called Laplace transforms. So it's a study of what Laplace transforms are. Well, they're a kind of transform named after Laplace, obviously. Okay. But for us, what they're going to mean for us is they're going to provide a method for solving certain types of differential equation. Okay. Now, in a lot of applied maths, a lot of mathematics, that really is the main enterprise that you're going about all the time. Any kind of problem in engineering or physics type setting or in any of the other sciences, often it's presented mathematically as a problem to solve, as a problem as a type of differential equation or a system of differential equations. And they could be ordinary differential equations. Ordinary differential equations means a differential equation where the function you're looking to solve for, or the unknown function is just a function of a single variable. Or the terminology PDE, partial differential equations, is one where the unknown function you're trying to solve for is a function of more than one variable. Okay, so the derivatives appearing in a PDE are partial derivatives. So I'm sure you've come across these in various ways up to now. And if you look at the third year options, there's an option on linear algebra and what's it called? Linear algebra, computational linear algebra and solving ODEs. So there's one that's focusing on ordinary differential equations, and then there's one partial differential equations, focusing on partial differential equations. So, this could, depending on the unit choices you make, this could be a large part of your third year diet of mathematics. And of course, often the way is that any kind of interest, or any kind of interesting maths problem or realistic maths problem, of course, the differential equations that you meet, they can't be solved. They can't be solved exactly. They don't have nice, easily expressed solutions which are made up of combinations of the standard functions like polynomials, rational functions, quotients of polynomials, or trigonometric functions, exponentials, and so on. They just don't have solutions that are a pretty combination of those. And for those differential equations, of course, so you can't hope to solve them exactly. But what you do hope to do is solve them approximately, or numerically, as the term goes. So the numerical analysis of these differential equations is the study of finding approximate solutions to them. There's nothing wrong with approximate solutions, because the methods that we have, we're able to make them converge. So if we want a solution with any given accuracy, we can set up the algorithms that we're using or set up the methods that we're using to produce solutions to that desired accuracy. But what we're going to be looking at here is not numerical solutions. We're going to be looking at exact solutions. So we are going to be looking at a special class of differential equations for which it is possible to obtain exact solutions, okay, in principle. And what kind of equations are they that we're looking at? They're linear ODEs. Linear ODEs, so in a single unknown function, which is a function of a single variable, and they're ones with constant coefficients. Now, what do all these terms mean? Well, constant coefficients is easy enough. It means these numbers multiplying the various derivatives of y here in this differential equation, these are just numbers, okay? Constants. And the linear, what does the linearness mean? Well, what does a linear ODE? Well, something is nonlinear. A differential equation is nonlinear if you see two different derivatives of the function y that are multiplied together. Two different derivatives taken to different orders that are multiplied together. Or you see a single derivative of a certain order of the unknown function y, which is raised to a power different than 1. So this ODE here in 2.2, this is nonlinear because we've got the function y itself, which is like the 0th order derivative, multiplied by the first order derivative, dy dt. So this is kind of non-linear behavior in the sense of, in the meaning of the term linear as used to classify differential equations. Okay, but something up here like this, which is just constant times the nth derivative plus another constant times the n minus 1th derivative. Continue it on down, a constant times the first derivative, maybe a constant times the unknown function y itself, and finally the term which doesn't involve y at all in the equation. That doesn't have to be a constant. That can be a non-constant function of t. So our solution method will be able to cope with functions of that type so long as the function g is relatively well behaved or relatively standard. Then we'll be able to deal with equations like that. Now, often these differential equations, often the solutions to them aren't unique. Often there's a whole family of functions which can provide solutions to them. In order to pin down a general solution like that to make it an actual fixed, unique function, often you need extra information. And that often comes in the form of so-called boundary conditions or initial conditions. Initial conditions are normally where the unknown function you're looking to solve for is some function of time, which is typically representing the evolution of some system from some beginning point in time into the future. So time equals 0, t equals 0 is the initial state of the system. And very often that is known. So very often, because of the setup or the context of the problem you're solving, you know the state of the system at time 0. So you know the value y of 0. So that's kind of partial information about the solution. And that initial condition very often is enough to pin down the solution of the ODE to be a single unique function. Or this information can come in the form of boundary conditions. So that typically arises, well, in this in this ordinary differential case, it could be that the function y, for instance, is representing the behavior of a vibrating string, say, like a string on a musical instrument. Okay, so there's an ODE called the wave equation, which represents what happens to a string when it vibrates. And there, what you do know about, so you're trying to solve for the motion of the string, so how the string is oscillating up and down. But what you do know about the string is that it's fixed at both ends. So the string on a musical instrument, it's fixed at one end because it's attached to the instrument, and it's either fixed at the other end when, think of a guitar, it's fixed at both points, or indeed, when you're playing any particular note, you're pressing the string down with the finger, so it's fixed at that point as well. So you know the position of the string at the boundaries of the string. You know the behavior of the solution function at the boundary of the area of interest. Okay? So that kind of information is called boundary conditions. And that very often as well is enough to pin down the type of solution to be a unique solution. Or indeed to restrict the possible family of functions that could be the solution. Okay, so what is this Laplace transform? Well, before we get into looking at exactly what it is, I want to try and explain the idea of using a transform to solve a problem and how that kind of works, or just give a simpler kind of way to think about that. And I'd like to do that by just drawing your attention to stuff you already know. And that's to consider the logarithm function. That's right. I mean, you guys maybe didn't encounter this so much. I mean, I certainly did. When I started school, everybody didn't have a calculator, so we still use some of the old-fashioned calculation techniques. So yeah, so I've Googled for log tables. Obviously, there's two types of things that come up. Only one of these is relevant to today's lecture. the logarithm tables. So what were these? I want a big one. I can show you. So log tables are tables showing lots of values of the logarithm function. Come on. Things like that. So why did people go to all this trouble to... So these were obviously developed in the days before mechanical or electronic computing devices. So why did people go to all these troubles to work out precise values of a certain function? And what did they use them for? Okay. Well, I mean, I hope you're aware of this. There's also, you know, so before they could just type into their calculator log of something, or why would you want to know the logarithm of something? Well, okay, there's many reasons, but one aspect of it I'm going to present to you at the moment is an observation. So if you think of all these old-fashioned mathematicians doing calculations by hand, there's an obvious thing is that multiplication is harder than addition. If when you were analyzing some problem, and some physics problem or engineering problem, if you just have to add up a load of numbers, that's fairly easy. You can do that fairly quickly. But multiplying numbers is an altogether longer process. And exponentiation, or raising a number to a power, is an even harder operation still. Okay. If your solution method for solving a problem involves lots of exponentiation, raising one number to the power of another, that's a bit of a drag when you're faced with that. If you want to raise 2.762 to the power of 3.45, oh God, it's a nightmare. You wouldn't want to do that by hand. But people had to do this kind of thing by hand, before they had calculation devices. So one aspect of the logarithm is a transform, we can think of it, or it's a transforming tool, let's just call it. It's not a transform in the sense that we're going to introduce a transform, but it's some kind of a tool which turns a hard arithmetic calculation, into an easier one. So how does it do that? For example, if I have to multiply together two numbers, A times B, so the thinking is that's hard. It's going to take me a lot longer to multiply them together than if I could just simply add them. But if I take a logarithm first, if I forget about multiplying A times B for the moment, and if I just take the logarithm of it, I try and work with that instead. Now, a key property of the logarithm, of course, is, what does that turn into? Log A plus log B. Yeah, so logarithm of a product is the sum of the logarithms. So you see that the hard problem of multiplication suddenly turns into an easier problem of addition. Which you can work with, which you can solve. So you can find an answer to, you can easily get the number C, which is the logarithm of A plus the logarithm of B, which is in turn the logarithm of A times B. And how do you get back to the answer that you want? Inverse of the logarithm, which is exponential, yeah. So you apply the exponential function to get back, and you get e to the c, which will be actually the value a times b. Now, why go to all this work when you could just multiply a times b and get them? Well, the idea is if someone does the hard work and generates those tables of logarithm values, and hand in hand with them will be table of exponential values. You shouldn't get any funny result for this. Hope it's all right. So there are similar things which are tables of the exponential function. Somewhere, if you find them. Or you can simply use the logarithm function, but the logarithm tables backwards, I guess. Yeah, sorry, I think it's really the same table, isn't it? Just reading the logarithm table backwards, looking for entries and reading off the column headings. So the transforming work and the inverse transforming work is done already. So these steps are just, there's no computational cost to these steps. You're just looking up pre-computed values, so to speak. But this calculation here is easier than this calculation over here. This way is hard, this way is easier. So you think of the logarithm, and hand in hand with its inverse, which is the exponential. You think of that as a tool which solves this problem. Okay? It lets you avoid doing the hard work of multiplying numbers together by instead adding numbers together with just two lookup operations to look up stored values of the functions, which obviously someone went to a lot of trouble to calculate originally, but once they did have them calculated, you can use them and reuse them. Yeah, obviously, there's the errors associated to this because these values here aren't exact values. They're obviously just accurate to however many decimal places. But if you're doing a practical applied maths kind of stuff, that doesn't really matter because you just get answers out which are accurate enough. And of course, there's a similar kind of picture to powers because another property. So also notice the property that the logarithm of a power of a to the power b, of course, has a simpler representation. That's a product of b with the logarithm of a. So a power is turned into a product. Okay? So it takes complicated stuff and it turns it into easier stuff. As long as you can achieve or carry out the logarithm and its inverse with the help of these pre-computed values, it gives a good tool for working with these things. Okay? And that's how that's one use to which these logarithm tables were put. Before people had calculating devices, the term calculator actually referred to a person. These would be the assistants of, the scientists, and scientists would give the calculations to them to do, and they'd work away with the tables and produce answers. So it's this kind of a picture that we're going to introduce the Laplace transform into. Okay. Is everybody okay with that diagram? Can I take that away? So now come to consider our differential equations. Here's a typical differential equation like the one we gave in the notes. Okay. So those y's, those are the various derivatives of y here. So y brackets m refers to the mth derivative of the function y. Y is a function of t. So that's our ODE which we wish to solve. But the thinking is that going straight to a solution, that y of t equals some kind of nice function of t, that this is hard. So instead, we're going to, well, we're not using a logarithm, but we're using a tool called a transform, which is going to do a similar type of job. So we're going to take the Laplace transform. You see, the reason the ODE is hard to solve is because it features all these different derivatives of y, all these derivatives of different orders of y. And there's no way to combine those all together into a single object involving y, which you can then somehow turn into a solution, y of t equals whatever. Okay, so when we take the Laplace transform of this whole equation, it gives us a new equation. So this is the transformed ODE. And what the ODE transforms into is some kind of object which features it transforms into an equation which features objects, I'm calling them for the moment capital Y of S. We'll see in a moment exactly what they are. And they have coefficients. I'll call them capital A's for the moment. So these capital A's these are polynomials in S. So part of the transform involves introducing a new variable called S. The variable t kind of disappears for a moment, disappears from the picture, and instead you get a new equation involving a new variable S. Okay, we'll make all this much more concrete in a moment. But this solving step, we then solve this equation for the unknown function capital Y of S. Capital Y of S is related to the Y of t. We get some nice description, a nice enough description of capital Y of S as a function of this new funny variable S. And once we have this in a suitable form, we can then apply what's called we just apply the inverse Laplace transform. Which will take our strange function capital Y of S and turn it back into the little y of t. And it's this route here around this diagram which is easier than going, which is possible to do compared with going straight to the solution from the ODE. But the one key feature to notice about it is, in the original ODE, we had several derivatives of y, all derivatives of different order. But the way they transformed under this Laplace transform process, whatever it is, and we'll see in a moment exactly what it is, the way it transforms is the different derivatives of different orders, they all transform to different multiples of the same function, capital Y of S. So really, it's the same unknown function which is occurring in the transform of each of the terms from the ODE. It's just the same function, capital Y of S. And that's what makes it possible to solve for this, to solve the equation, to solve the transformed equation, to get a nice description of Y of S. Okay. So in this way, the Laplace transform provides a tool to solve these ODEs. If they're of a suitable type, if there are these linear ODEs with constant coefficients, except maybe the the coefficient not dependent on y. That can be a non-constant function of t. As long as that function g of t is relatively standard, and we know how to deal with it, the Laplace transform method should allow you to find the solution of the original differential equation. Okay, so that's a lot of talk about the transform without actually, without actually saying in detail what it is. So we'll turn to that issue now. Any questions? I mean, I know it's all a bit vague and hand wavy because we're just trying to give a view of the whole thing without getting into detail what the thing is. Any questions at the moment? So I want you to watch out for when we meet the results, which tells us this. It's this feature, the fact that the derivatives of different order, they all transform to more or less the same unknown function, capital Y of S. So you can literally simply collect together all these terms. It's just some big long polynomial in S times Y of S. Okay, so it's a lot easier. So you can collapse all these terms into one here, because they all have the same common factor of the function capital Y of S, whereas you can't collapse all these terms in the original ODE into one, because they're all derivatives of different order of the function Y. Okay. So here we are back in the notes. So let's meet the transform and see what it is. Okay, so I switched from talking about y's back to talking about f's. Okay, so we'll look at definition 2.1. This is the definition of the transform. So when we say a transform in this setting, what we mean is it's an operator which takes you from a function depending on a variable t, and it takes you to a new function of a new variable. Okay? So we have a function depending on a certain value of t, and we apply a transform, which for us will be specifically the Laplace transform, and we get some new associated function. So we get a new function and this new variable introduced. Okay, so it's the general picture of what a transform is. And it often has an inverse transform, which takes you back the other way. Okay, so it's taking you from one function to a new function of a new variable. So let's have a look at what it is. So f of t, little f of t, we're going to think of as our original function. And you think of this as this is kind of this, the little f of t could be the unknown function appearing in an ODE, in a differential equation. And this is what the Laplace transform is. Okay. Now there's various bits of notation for it. One common notation is this curly L operator. So it's a script L. That's how it's traditionally written, like a handwriting script L. So this stands for the Laplace transform operator. So here it is applied to a function. It's a certain integral with respect to t. We're integrating over all t values from t equals 0 onwards. So we're integrating from 0 to infinity with respect to t. And we're integrating a certain product, so the function values f of t are in there. And there's an exponential e to the minus s times the variable t. So here you can see the new variable introducing. So you have this integral. The value of the integral doesn't depend on t. T is integrated out, if you like. Okay? All values of t are taken into account in the calculation of this integral. But if you provide different values of s, the integral, it changes value, okay? Because you're dealing with a different exponential. Other types of notation or other, forms we use for this So it's also notated as variously, it can be written as the original function letter with a bar over it, but this time applied to the new variable. So f bar s could also refer to the Laplace transform. Or another convention is to use lowercase letters for the function, for the original functions, so a little f or a little g, and just use the uppercase letter for its transform. So those are different conventions that are used. You'll see them appear variously in different books or sources. And I think in the notes, I tend to use a kind of mixture of them all. But sometimes certain notations are more suited to pointing out different aspects of it. Because sometimes it's helpful to think of the transform as a kind of operator in itself. And you think of the transform as its own kind of object, the operator. So sometimes it's useful to have a specific letter to refer to the operator. So L is the operator. If you're just using little f and capital F, the operator becomes invisible. There's no letter to represent the operator necessarily. So it's a bit hard to talk about properties of the operator. So I kind of vaguely have a preference for the script L notation, but then you don't want to be writing your new equation and having to write script L brackets f of t all the time. Just for ease of use and for economical writing, it's sometimes a lot easier just to use a capital F to refer to this thing, okay? Okay. Now, in general, this new variable can be a complex variable. So S can be a complex number here. We won't make too much of that, because for us, the main interest for us for studying this transform is the method for solving a differential equation that it provides. Okay, so the fact that this new variable S you're bringing in is a complex variable as opposed to a real variable, we won't kind of chase that property too much. And of course, when you see a thing like this, the integral from 0 to infinity, you immediately have a question, well, does that make sense? Do you get anything sensible out of integrating something from 0 to infinity? Because often you don't. Okay, if you integrate a polynomial function, if you integrate a polynomial in t from 0 to infinity, it won't be convergent. You'll get just the answer infinity for whatever function, whatever polynomial function you put in there. So it's a question, is this, does this refer to anything? So that's what I'm discussing there. Of course, a function only has a transform if the integral in 2.4 converges. Now, it will converge for most of the kind of standard functions we meet. And the reason it converges is because of the presence of the exponential factor here, e to the minus st. Okay, and at least for values of s for real positive s, i.e. s greater than 0, the exponential factor e to the minus st will converge rapidly to 0 for positive values of t, and you're integrating over positive values of t. So the presence of this exponential factor will mean that, at least when when s is positive and t is always positive in the integration, so you're taking the exponential of a negative of a positive. So you're taking the exponential of a negative number. And so as t increases, the size of this negative exponent is getting large very quickly. So the exponential is going to converge to 0, okay? Because e to the power of minus a large number, e to the minus 100, or, that's extremely tiny. And it only gets smaller and smaller, it converges to 0 as t gets larger and larger. So this makes the integral converge for, and I'll put it in quotes, but for most functions f. For most functions f. For one of these integrals to not converge, the function f would have to be increasing faster than an exponential. The exponentials increase fairly fast. So in order for the increasing nature of the function f to overcome the decreasing nature of the negative exponential, f would have to be increasing fairly rapidly. Okay. So for most of the functions we're going to meet, these integrals are going to converge. Okay, so let's try and look at a couple of quick examples. Then maybe even hit a proof of our first property of the Laplace transform. So let's start trying a few standard functions f. So you see in example 2.2 there, we take the constant function. We're looking at the constant function, f of t equals 1, the constant function with constant value 1. We'll try and take its Laplace transform. So according to the definition, I'm evaluating this integral where f of t is replaced by the function. Well, this is just the constant function 1, so I'm just replacing f of t in the definition with the constant term 1. So it's really just an integral of e to the minus st. E to the minus st has you can integrate an exponential, it's just itself, e to the minus st, and we're dividing by minus s, because that's the thing multiplying the t in the exponent. And you evaluate this at 0 and infinity. Well, really we need to add the condition s is bigger than 0 here. So just as I've said there, so in example 2.2, we assume that s is bigger than 0. That s is a real quantity and that it's bigger than 0. Well, if s is bigger than 0, then when you evaluate e to the minus st at t equals infinity, well, really you're taking the limit of e to the minus st as t goes to infinity. That's going to be equal to 0. Okay, so you're taking the limit of e to the minus a power. Okay, e to the minus of a positive number. Okay, so that's going to go down to 0. And then when you evaluate it at t equals 0, you just got e to the 0, which is 1 over minus s. And you're subtracting that because it's the lower limit. So you just get the quantity 1 over s. So that's our first result, that the Laplace transform of a constant function, well, the constant function 1, is simply 1 over s. So it's going to take us a while before we can actually put the transform to use to solve some ODEs, because we have to build up a bit of knowledge about the transform first. Look at what some transforms of some standard functions are and find out relevant properties of the transform that's going to make it work as a solution to it. The next function we'll try is the function f of t equals t. Okay, so an order 1 polynomial term in t, f of t equals t. We'll try and take its Laplace transform. So we're integrating 0 to infinity, e to the minus st times t dt. But can we do that integral? Yeah, that's just an integration by parts integral, integrating the product of t times an exponential. So you recognize that you can do that by integration by parts, because when you differentiate the t factor, that's going to differentiate to just a constant. So you'll be able to relate the original integral to just an integral of the exponential, which you'll be able to do. So first I rewrite the integral as t times a derivative of something. And because it's an exponential function, it's easy to write down what e to the minus st is the derivative of. It's the derivative of e to the minus st over minus s. And then you just apply integration by parts. So you get the t times the exponential evaluated, and then you're subtracting the integral of e to the minus st. But now, because of the presence of the t factor here, when you evaluate this when you evaluate it as t goes to infinity, again, you get 0 because of the presence of the exponential. And when you evaluate it at t equals 0, you get 0 because there's a factor of t there. So it just comes out to be this integral of the exponential, which we can do. I mean, in the previous example, we did the integral of the exponential and we got 1 over s. So here we're going to get 1 over s again, but there's this extra factor of s here. 1 over s there, so you're going to get 1 over s squared. So that's our second result. That the Laplace transform of the function f of t equals t, which is the identity function, if you like, or the order 1 polynomial term, is 1 over s squared. So the Laplace transform of the constant function is 1 over s. The Laplace transform of t is 1 over s squared. Could we hazard a guess at what the transform of t squared is? Good guess. 1 over s cubed, not quite right. It's not a 1 over s cubed. It is a something over s cubed. So we'll find out, but you know. Sorry? N. What's n? I don't see any n's anywhere. It is going to be 2, yeah. Did you look that up in the table on the following page? Yeah? Good. Very good. It's actually 2 over s cubed. And there's a pattern. The transform of t cubed. So you were saying n because there's an n in the formula on the who was saying the n? You should have read out the right answer with n equals 2. Anyway. Yeah, so it's some kind of n factorial type thing over s to the n plus 1, as you can see in the following page. But we'll be proving that in due course. So yeah, so what they were looking at is on the following page. This is the equivalent of the is the equivalent of the log tables we saw. So the log tables we saw before did all the work of calculating the actual values of the logarithm function. Here we will have at our disposal, and crucially you'll have this in the exam when it comes to it, and you'll be able to use this. This is a table of Laplace transforms. So down the left-hand side, we've got a whole lot of standard functions, various kinds. And on the right-hand sides, we've got their Laplace transforms. And we'll be proving many of these and proving properties which are used to calculate many of these as we go along. And this is a kind of family of important properties of the Laplace transform, which we'll be coming to in solving. But in 2 minutes, we'll prove our first theorem, a 2-minute theorem. This transform is a very nice property. It's linear. You're always on the lookout for linear stuff in mathematics because linear stuff is quite easy. It's good behavior when operations behave linearly. And this says that if you take the Laplace transform of a linear combination of two functions, what's the answer going to be? The Laplace transform of a linear combination is the linear combination of the individual transforms. Two-minute theorem. How is he going to prove this in 2 minutes? 1 minute by now. How the hell is this true? In one line. Well, in one line, the Laplace transform of this thing on the left-hand side that's what the left-hand side is. This is just integration. And what do you know about integration? Well, you can multiply out that bracket in the middle, split things up. Integration itself is a linear operator. The integral of a sum of two functions, you can integrate each of them separately and then add their answers together. That's stuff you already know. So you can move the integral, move things around a bit, to use the technical term. you can turn the integral into this. Using properties of integration you're already equipped with. Integration is a linear operator. So this alpha, which is just a number, can zip out to the front, and this beta can just zip out to the front, and integrating the sum of these two things, you can just split them up. But of course, what you're looking at there is exactly alpha times the Laplace transform of f plus beta times the Laplace transform of the function g. So that's the proof. Well, okay, it's not, there's an awful lot, you could ask, well, you have to prove that integration is linear. But, assuming that we know about integration and we know about its properties, the linear nature of integration operator gives to the Laplace transform operator the linear property as well. Okay? So that's going to be nice to know. So the justification is since integration is linear. That's the point. Okay, I better stop there. 10 minutes to the hour. So we'll continue with this